All right, so I wanted to make a quick video to give you guys a little bit more support with the potential energy diagrams. It looks like a lot of people were having trouble with workbook 13.3. This is one that is going to be quite there will be similar questions to this on your upcoming quiz for this week, as well as your exam that we have coming up soon. So I wanted to spend a little bit of time reviewing some of the key information from potential energy diagrams, what we're looking for, and then we'll look at workbook 13.3 a little bit together. So I'm not going to talk a ton about what these values mean in this video. For that, please go back to the previous recording where I went over potential energy diagrams the first time. In that, I spent a lot more time kind of talking about what each of these different values mean and how we interpret them. But today, I really want to focus on just how we read this graph and how we find the values that we're interested in. So when we're looking at a potential energy diagram, there are always 5 things that we're looking for. We're looking for the enthalpy of the products, the enthalpy of the reactants, and the enthalpy of the transition state. These are all going to correspond to a particular height on the graph. The reactants will always be first on the left side because we're looking at a potential energy diagram showing us the reaction progress. So we always start with our reactants on the left and move towards our products on the right. And then the highest point on the graph is always going to correspond to the transition state. So those are the 3 values that we find based on the height from where we find them on the graph. And then we have 2 values that are found using subtraction. So they are indicated on the graph as a range. So we know that the enthalpy of the reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. So on the graph, we indicate that as the range between the enthalpy of the products and the enthalpy of the reactants. Activation energy is the amount of energy that it takes for us to get from our reactants up to our transition state. That's that initial boost of energy we need for the reaction. And so we find that also as a subtraction between the enthalpy of the transition state and the enthalpy of the reactants. So again, we indicate that as a range on our graph. So I'm going to show you a couple examples and then we'll look at the actual workbook. So here is just a simple potential energy diagram. First thing I notice right away is this is an exothermic reaction. I always check with myself before I start looking for anything and ask, is this exothermic or endothermic? And I know that it's exothermic because the enthalpy of the products is less than the enthalpy of the reactants. That means when I do that subtraction, I'm going to get a negative value. Okay, so now let's look for all of these 5 key points. So my enthalpy of my product is always going to be this value on the right that I see here. Enthalpy of my reactants is going to be here on the left. So if I'm looking for these actual values, I'm looking for their height on the graph. So I'm finding the numbers that correspond to their height here. That would give me my enthalpy of products and reactants. My enthalpy of my transition state is going to be probably right about here on my graph because it corresponds to this height right here. And then my 2 ranges that I'm looking for, the first is the enthalpy of the reaction. Again, that's always going to be between my enthalpy of my products and reactants. So in this case, that's going to be a pretty large value because there's a pretty significant height difference between those. And it's going to be a pretty large negative value in this case because my reaction is exothermic. And then my transition state is going to be indicated between the range between my reactants and my transition state point up here. All right, I'm going to show a couple more examples here. So looking at this potential energy diagram, this is very similar. The only difference here is that the difference between the products and the reactants is much smaller. So this is still an exothermic reaction. It's just going to be an exothermic reaction that releases less heat than the first one. But again, my products are still lower than my reactants. So I'm still going to get a negative value for delta H. It's just going to be a smaller negative value. So this might correspond to something like negative 100 kilojoules over here, whereas maybe this is negative 25 kilojoules over here. So this would be releasing 100 kilojoules of heat, whereas on the right, we'd be releasing only 25 kilojoules of heat. All right, and then I just wanted to show a couple more examples just to see kind of how all of this can look. So here I've got an endothermic reaction on the left. Notice it's really similar, except it looks like it's flipped, like a mirror image. And so now I'm going to pull my list back up over here. So now we can see we still look for the same 5 values. The place where a lot of students get confused here is in those ranges. So we can still find right away, here's my energy of my reactants. My products would be about here. They correspond to this height on the graph. So they're about here. But where students sometimes get confused is finding the enthalpy of reaction and the activation energy when we're kind of changing between endo and exothermic. So in this reaction, my enthalpy of reaction is still going to be the difference between the products and reactants. So here we drew that on the left. Here we drew it on the right. That's just because it's easier to draw it on those sides. You could draw it wherever you wanted, as long as I can tell that you're saying it's the difference between reactants and products. Difference between reactants and products. And then my activation energy on this graph, so we said activation energy is always the range between the reactants and the transition state because it's our initial boost needed to start this reaction. So here, this is my transition state up at this point. My reactants are down here. So this big range is going to be my activation energy. Ooh, sorry, I'm using my mouse to draw that, so it's pretty ugly. But there's my activation energy. And so you'll notice on an exothermic reaction, our activation energy tends to be pretty small, a little bit bigger in this kind of situation. Whereas in an endothermic reaction, our activation energy tends to be pretty big. And this can start to make sense if we think about what's happening with the reaction. This is a reaction that's absorbing more energy than it's releasing. So it makes sense that this initial energy boost needed would be a larger amount of energy needed into the reaction. All right, and then I just have one more exothermic example just because I wanted you to see one that kind of is structured a little bit differently. Sometimes these are a little curvier in the way they're drawn. Sometimes sometimes the reactants and products enthalpy is drawn just as a straight line, like as in these. So here's one more exothermic. We can see here's my reactants are on the left, products on the right. My transition state would be here. And then my enthalpy of reaction is the difference between products and reactants here. And my activation energy would again be from the reactants to the highest point. So in this case, it would just be about here. And I can kind of draw a dotted line here if I want to indicate where that height is coming from. Okay, so now let's look at the actual workbook assignment that you guys have with these. So here is the potential energy diagram I was asking you about. And so again, first thing you want to do is ask yourself, is this an endothermic or exothermic reaction? And we do that by thinking about the enthalpy of the products and reactants. So here, my enthalpy of my reactants is lower than my enthalpy of my products. So we ask ourselves, where is this energy coming from? How are we ending up with more energy than we started with? We have to put energy into this reaction. So this is an endothermic reaction. So I know that because the energy of the products is higher than the energy of the reactants. So let's go through these actual questions. First one says, which letter, A through F, represents potential energy of the products? So we said the enthalpy of the products is always going to be on the right side of the diagram. So in this case, that's going to be the point at Z. That's going to be the height at E. So Z is just telling me what my products are, kind of what my reaction looks like. So this would be E. E is showing me this is the height of my products. It's all the way up at the product point. Which letter A through F represents the potential energy of the reactants? We said the potential energy of the reactants is always going to be on the left side of the diagram. It's what we're starting with. So that's going to be A, that height that gets me all the way up to my reactants, which in this case are some chemicals called X and Y. That's going to be A. Which letter A through F represents the activation energy of the forward reaction? Don't worry about forward. We'll talk more about forward and reverse reactions in our last unit. So the activation energy is the range between the reactants and the transition state. So my reactants were down here. My transition state is up here. So my activation energy is going to be the difference between this highest point and this point where it says x plus y. So that's going to be B. B gives me that height from my reactants all the way up to my transition state. All right, if the enthalpy of the products equals A and the enthalpy of the reactants equals B, what is the enthalpy of the reaction? So I'm saying if I give you some value for the enthalpy of the product and I give you some value for the enthalpy of the reactants, what's the enthalpy of the overall reaction? Now, I don't actually even need the graph for this one. I know enthalpy of reaction is equal to enthalpy of products minus reactants. So that's in this case going to be A minus B. And these are not the same little a's and b's as we see on our graph. This is just corresponding to some value. Maybe products is 70 kilojoules, maybe B is 30. So to figure out the enthalpy of reaction, I would do 70 minus 30. All right, and we already talked about this reaction. We said this was endothermic. And this is how can you tell? So the way we said we know is because the energy of the products was greater than the energy of the reactants. All right, so here's another diagram. Again, very similar. We can always think through these 5 values, and these are the exact same values that I'm asking you about here. So let's find them on this graph, but now we're going to put some actual numbers to them. So first one asks you about the enthalpy of reactants. So we said that's always going to be what's on the left side of the graph. So here, that's my first kind of flat line. That's at 20 kilojoules. The enthalpy of the products is always going to be on the right side of the reaction. That's at 50 kilojoules. The enthalpy of the transition state is always going to be the highest point on the graph, which in this case is going to be 100 kilojoules. So we said these 3 I can always find as heights on the graph, and then these last 2 I find using subtraction. So my enthalpy of my reaction, my delta H, is going to be equal to the H of the products minus the H of the reactants. If I wanted to look at that on the graph, it would be, again, if you can see my mouse, that would be this height right here, products to reactants. So I'm going to do enthalpy of the products, which is 50, minus enthalpy of the reactants, which is 20. So I'm doing 50 minus 20 gives me 30 kilojoules. That's a positive number. So that's the other way that I can tell myself, okay, delta H came out positive. That means this is endothermic. And then my activation energy is how much energy is required to start this reaction. So it's between the reactants and my activated complex, my transition state. So in this case, that's going to be all the way up at 100 minus 20. If I was to show this as a height on the graph, it would look like this. So we're going to do 100 minus 20 here. It gives me 80. All right, so hopefully seeing that helps you kind of get through and feel a little bit more confident. If you still have any trouble with these, please join me for office hours and we can talk more about any of these practice questions or anything else that you've been having trouble with in this unit.